Hi everyone, my name is Vismaya VS and here I will be presenting my work on Degn Harrison map, Dynamical and Network Behaviors with Application in Image Encryption. This work was done under the supervision of Dr. Shishranga Muni, Digital University, Kerala. In this presentation, we will explore the Dane Harrison model, its dynamics, how it behaves in network, and its use in encrypting images. Let's begin with a little background on why the Dane Harrison model was developed and what makes it unique. Dane Harrison model was initially developed to explain oscillations in the respiration rate of Klebsiella aerogenus bacteria. This bacterium exhibits periodic fluctuations in its respiration rate under specific conditions, which is what the model aims to capture. Over time, researchers realized that the discrete version of this model not only applied to biological oscillations but also exhibit complex dynamical behavior such as bifurcation and chaos. Oscillations and chaos are common in many real-world systems, from chemical reactions to biological processes. And understanding these behavior is crucial for fields like biology, engineering, chemistry, and cryptography. And now that we know the origin, let's dive into the mathematical formulation of the model. This is the equation for the Dane Harrison model. And here Xn represents the concentration in the reservoir and Yn represents the reaction concentration in the chamber. And A and B control the rate of change of Y and X, and the delta update rate controlling how quickly the system evolves. And Q is the parameter adjusting the strength of the nonlinear interaction between Xn and Y. This nonlinear interaction is crucial for the system to exhibit chaotic behavior. And next, let's look at the system's equilibrium or fixed points, which help us predict long-term behavior. And what are fixed points? A fixed point occurs when the system reaches equilibrium, meaning the state no longer changes. Mathematically, this means solving for extra and y star where the system remains stable. And if both eigenvalues, that is lambda 1 and lambda 2, of the system are less than 1, the system is stable. And this figure is the stability triangle, where the blue triangular region represents stable points and dashed lines are representing the saddle points, and the system will diverge outside the triangle. However, not all fixed points are stable. Some points, known as non-hyperbolic points, behave more unpredictable. A non-hyperbolic fixed point has at least one eigenvalue with a modulus of 1, which means it had to determine stability. Such points are often indicate the outset of complex dynamics like bifurcations. And in this figure, the yellow line shows non-hyperbolic points where we need further investigation beyond linear stability. And another important concept is non-invertibility, which we will explore next. That is, Non-invertibility occurs when multiple initial states produce the same act, creating a folding effect in phase space. Here, the red curve divides the sway space into two regions, that is Z1 and Z3. And this non-invertibility contributes to the chaotic behavior of the system. Let's see how these fixed points and non-invertibility manifests a bifurcation structure. A bifurcation is when the system's behavior changes as a parameter is aware. These are the types of bifurcation seen in this model. That is spirit doubling bifurcation, that is a saddle state becomes unstable and splits into two oscillating states. And is saddle node bifurcation is the two fixed points also collide and annihilate each other. Last one is the Neyman-Zecke bifurcation, which leads to quasi-periodic orbits. And this is in this figure, A shows one parameter bifurcation diagram, and B shows the corresponding layup under exponent spectrum. And here we can see how variation in A, variation in the parameter A changes the behavior of the system. Here in A, it's a Pareto orbit. When the Pareto orbit undergoes peridoubling bifurcations, it's become Pareto 4 orbit, and gradually it turns to a chaotic trajectory. Now let's see how the Degn Harrison model uh, behaves when two parameters are varied simultaneously. Here, the different regions indicate stable and chaotic behavior, and the bifurcation boundaries mark transition between these states. The figure shows the two-parameter diagram and its corresponding bifurcation diagram. Now let's see how the Dynamical Harrison model behaves in network using the ring star topology. A ring star network combines a ring structure with a central hub, balancing local and global interactions, and a star network. Uh, Here, these are the coupling parameters. Sigma for the ring coupling strength and mu is the star coupling strength. By tuning these strengths, we can observe different behavior like synchronized, unsynchronized, and a chimera state. These are the spatio-temporal patterns observed in the Degn Harrison model. We got synchronized state, unsynchronized, chimera states, traveling wave, and two cluster state. The heat map obtained for ring star network where the first one shows the synchronized state, B is the unsynchronized state, C chimera state. These are the heat map obtained for the ring network. Here is the synchronized state, B unsynchronized. This is a class 2 cluster state, and this one is the D1 is the traveling wave. These are the heat map for the star network, where A is the synchronized state, B unsynchronized, and C is the two cluster state. Let's talk about how the chaotic behavior of the Dane Harrison model can be applied to secure image encryption. Traditional encryption algorithms like AES and TEX are excellent for text but struggle with images because images are large data sizes and inherent redundancy. This is where chaos based encryptions come in. Chaotic systems like the Dane Harrison model are highly sensitive to initial condition and system parameters. Even a small change in the input causes significant differences in the output. This makes it extremely difficult for attackers to predict or reverse engineer the decrypted data. Unpredictability and nonlinear dynamic of the chaotic system provide robust security by scrambling the pixel values in a non-reversible way without the correct decryption. The process includes generating the chaotic sequences from the Dennison map, then using these sequences to scramble pixel values, and then reversing the process for decryption. In the figure, the left one on the left, we see the original image, and the middle image is the encrypted version where the contents are completely scrambled, that is, pixels are scrambled. On the right, we see the descripted image with perfectly matching the original. Here for the security analysis, we use 7 methods: entropy analysis, correlation analysis, anomaly detection, histogram analysis, robustness to noise analysis, differential attack analysis, and key sensitivity analysis. These are the values we got for entropy analysis of Lena match, both scaled and colored, and also the anomaly detection. Here we calculated the MSC and SSIM for both grayscale and colored image of the Lena. This is a histogram analysis of this grayscaled image and colored image. And this is the key sensitivity analysis. The algorithm is not able to decrypt the image because of slight change in the. To conclude, the Dane Harrison model provides a powerful framework for understanding and applying chaotic dynamics. The model, which originated in biology to explain the oscillation in bacteria, exhibit complex dynamical behavior, including chaos and bifurcation. We saw how this dynamics extends to network, where the ring star topology enables interesting behavior such as synchronous state, camera state, traveling wave, and two cluster state. Finally, these chaotic signals generated by the models are highly effective for image encryption, and they provide robust security through unpredictable scrambling, resistance to noise, and sensitivity to encryption key. Thank you for all your attention.